All right. So today we are going to be talking about structural relations. Now, structural relations can be a little, as I've said before, a little dry because we're not looking so much at natural language. We're looking at just abstractions over the representations of language. We're looking at the abstractions over a tree. So what we're going to be looking at today, we're not going to be looking at real language data. We're going to be looking at the ways in which things are represented on a tree. Now we're going to utilize this to sort of help us better understand some concepts we've already addressed and to help us understand future concepts. So these are really important. And this is going to help us make sure that the hypotheses that we develop within our framework and within our theory are as precise as they possibly can be. And that's really important because precision allows us to make falsifiable hypotheses, and that's how we do science. So we're going to need to keep all of this in mind as we do this. Now, I want to start off by just looking at some of the really, really basic parts of a tree. I also want to note that I've already used some of this terminology because it's really hard to do syntax without ever talking about, ever using these terms. So you're probably already familiar with some of these terms just through sort of osmosis or other sorts of connections, but we're going to more formally define it today. So a tree is made up of nodes and branches. And we can define our nodes in multiple different ways. We can talk about terminal nodes, and terminal nodes are the nodes really at the very base of the tree. Now, it doesn't matter how you draw your trees. If you notice, like I have B way up here and M way down here. Some of you may draw your trees where all of your terminal nodes are on the same line. That's totally fine. This doesn't matter. It's about whether or not these nodes have anything coming out of them, anything further coming down beyond, like, let's say, their lexical item. Again, this is a key point as to why we don't have that line connecting our label to our word. So let's say if we have a noun, we don't have it go from N to dog, for instance, because that N is a terminal node. So the terminal nodes are sort of the bottom of the tree. They are non-branching nodes. Branches are the lines that come out of the other parts of the tree. So they don't have any branching. They don't have any branches coming out of them. That's also pretty straightforward. So we can have terminal nodes. We can have non-terminal nodes. So those are terms that we're going to be utilizing. And then we also have a special node that we refer to as the root node. And the root node is the node that is the root of the entire structure. It's the non-terminal node which has no other nodes above it. So from which everything else branches. That is our root node. All of these other nodes are so nodes like B, D, G, H, L, M, and N. Those are all our terminal nodes, and nodes like A, C, E, F, and I are non-terminal nodes. And then the lines themselves are our branches. Now, just a few things with branches. By rule, branches do not cross each other. Now, sometimes you might see a poorly drawn tree. So let's say we have a tree like this. Where someone, I'm trying to break, just draws like just poorly draws the tree. Now, this is bad drawing Now, if they don't intend for I to somehow precede G, this is just bad tree drawing. This is not a real violation of sort of the fundamental rules of non-crossing. However, if they are, don't do it. Don't do it. It's bad. You don't want to do this. You want your trees to be cleaner than this. So yeah, do not do this. But it's much worse if you're trying to do it because you need the word order to come in a different way. That probably is saying that you're doing something wrong with the phrase structure rules, you're doing something wrong with the constituency, or if you're really sure that your phrase structure rules are right, you're really sure you're getting the constituency right, and the word order is still not coming out right, then probably the framework that you're working in, the model needs further revision, which, occasionally there will be problems like that where we're going to be challenging you to reconsider this. But our branches do not cross. That's sort of a fundamental notion of the syntax that is really important. Okay, so that's the basics of a tree. We've spent a lot of time over the last couple videos talking about constituency, and I've talked about how our phrase structure rules represent constituency. And they represent constituency through the notion of the sort of notion of these nodes. Now, there's two ways we can sort of formally define the notion of a constituent. A constituent to do that, we're going to have to sort of think about what this means. So let's look at some of these elements of this tree and think about what the constituents are. Well, we can look at, let's say E here. If we were talking about a constituent E, I keep clicking on this to change color and it's not working. There we go. If we were looking at a constituent E, the constituents in E would include all of the elements that are below E, essentially. All of the elements that are in here. And we can formally define this. And we're going to formally define this using a notion of domination. And so domination is just this idea that you go to a tree, you look at the node, and then you look at all of the pieces that are below, that trace down the trace down on the tree. So we follow these branches down, and so E is going to dominate F, it's going to dominate G, it's going to dominate H, it's going to dominate I, it's going to dominate L, it's going to dominate M, and it's going to dominate N. So those are the nodes that E dominates. And we can then define what it means to be a constituent through this notion of domination. So what does it mean to be a constituent? Well, it means that you are part of this set. Not only part of this set, you are the exhaustive part of this set. So to be a constituent, you have to be all of these elements. So we're going to define this as exhaustively dominated by a node. All of the terminal nodes that are exhaustively dominated by a node. That's going to be our definition of a constituent. So the constituent F is going to be all of the nodes that are exhaustively dominated by it. So that's going to be G and H. Now you might notice that we're going to run into maybe a slight problem with this definition because I've also mentioned that nodes themselves are constituents. So G is a constituent, H is a constituent. So we'll have to either say that nodes dominate themselves or allow for some other means by which terminal nodes themselves are constituents. But for the larger scale constituents, the ones that we're mostly talking about, we can use this notion of domination, and particularly exhaustive domination, to define our constituents. You'll hear me use this term, and I've used this a lot in the video, something being a constituent of. And this is sort of just flipping this around. So to be a constituent of something really just means you are dominated by that thing. So when I talk about is I a constituent of E, I'm just looking, well, is it below on the tree? Can I trace a line back up and see that it is in the sort of domination? And the answer is yes. So I is a constituent of E, but D would not be a constituent. So that's going to help us sort of more formally define what it means to be a constituent. So I want to move into a few related areas. We'll utilize this terminology in a more informal sense, and you'll see this terminology used a lot. We have for whatever reason, the history in linguistics, and this actually doesn't just this isn't just purely in linguistics. This is in other mathematical fields that use these types of representations. But the history is to represent the relations of these types of structures through a maternal family tree, essentially. So we'll often use informally. These are informal definitions, terms like daughter, mother, and aunt. We'll talk more about aunt in a second. So what we're talking about when we're talking about those relations is we're still talking, particularly when we're talking about mother and daughter, is we're talking about domination relations. But we're talking now in a more immediate sense. So to be something's mother, you are in a direct domination relationship. So E, for instance, is the mother of F and I, because it is exactly one branch away from F and I and dominates it. A dominates immediately B and C, so it is their mother. B is a daughter of A. F is a daughter of E. D is a daughter of C, and so forth. So those are the mother-daughter relations. Again, you'll actually probably run into that terminology more frequently than domination. So the mother-daughter description is this informal description is used more frequently than the technical definition of domination. But motherhood, it can still be used to help us define what it means to be a constituent. We can also talk about nodes being sisters, and that will help us then ultimately define what it means to be an aunt, obviously. But nodes that are sisters are nodes that share a mother, not surprisingly. So, for instance, our nodes D and E, they are sisters because they share the mother C. Our nodes L, M, and N are all sisters because they share the mother I. Same with our nodes D and H. They share the mother F. So that is our sisterhood relation, and we look at do they share a mother? If they share a mother, then they are sisters. with our notion of sisterhood defined, we can then define a notion of what is referred to as sister precedence. Now, I'm not going to spend a lot of time on sister precedence, but for some of you, you might be interested in this a little bit more. But this is a way that actually helps us more formally define how we can get our final word order. So far we've sort of built a theory that allows us to define, that just basically says the words come in the order that they come in. And that works well enough, but with sister precedence, we're cutting that down into a little bit more of a fine-grained notion. So we're still saying that the order of the nodes matter, but we'll talk about nodes sister preceding each other. So that will mean, for instance, that G will sister precede H because G precedes H and they're in a sisterhood relation. B will sister precede C because B precedes C and they're in a sisterhood relation. And it's actually the fact that B sister precedes C that will ultimately make B precede the terminal node D because of the domination relation. Again, I'm not going to worry so much about how the linear order stuff all plays out, especially since really with the framework we're building right now, the terminal nodes just fully represent our linear order. So it's really not going to matter for that much for us, but it's a relation you may want to be familiar with. But then we get to the big one, and I do mean the big one. It's not that complicated of a relation, but it's one that sounds more difficult than it is. And this is the relation of C command. And C command is probably one of the most important syntactic relations to be aware of. So what C command is a relation of, I'm going to pause while the dog is barking, and I will resume in a second. I don't know if I paused. I hope I did. Well, luckily the dog didn't bark that long. So, yeah, I don't have the most sophisticated video editing software. So I do apologize if you just had 20 seconds of me just standing there. I'm also now just taking up too much time talking about it, so I'm just going to move on. All right, so C command. What C command is, and I'm going to provide the informal definition primarily because that's going to be the most useful for us. C command is a relation between sisters and all of the sisters' daughters. So, for instance, we can look at B. B is going to C command C and all of C's daughters. So basically, B is going to C command everything here. That is B's C command domain. And you'll hear that term used a lot. H, in contrast, will C command G, and G will C command H. So we'll talk about G and H being in a symmetric C command relation. B and C are in a symmetric C command relation because they C command each other. C will C command B. B will C command C because sisters C command each other. But a sister also C commands all of the sister's daughters. So B C commands D, but D does not C command B. So B and D are in an asymmetric C command relation. B C commands D, D does not C command B. And this relation is going to become absolutely vital for us, this notion of C command. So C command relations, again, basically you go up one node. That is not included in the C command relation. So it is a sisterhood and all of the daughters relation. That is C command. It's going to be very important for us. It's going to help us define a number of relations, particularly when we start looking at binding over the next few videos. But this is C command. So D, I'll just do a couple more. D, C commands E and all of E's daughters. So D will C command E, F, G, H, I, L, M, N. D is in a symmetric C command relationship with E and an asymmetric C command relationship with all of the other nodes down here. E is in a symmetric C command relationship with D and does not C command any other nodes. So yeah, look at the rest of this tree and see what other types of C command relationships you can find. But that is going to be, you're going to hear the term C command a lot. We'll talk a lot about C command. All right, I'm going to do a little bit more with C command in a video in the next couple days because it's so important. We'll look a little bit at some real language data in that one just to sort of drive in some of these notions. And I will close off again with a quote. I do apologize if there was that delay in there. I am working on developing some more sophisticated video technologies to improve these. Hope to have some options over the next couple weeks, but I do appreciate your patience and hope you're still getting something out of these. All right, so this is a quote from Epictetus. If you wish to improve, be content to appear clueless or stupid in extraneous matters. Don't wish to seem knowledgeable. And with that, I wish you again good health and safety during, yet again, these ongoing turbulent times. And thank you all.